morning, everyone, and thank you for the introduction. As a woman working in technology, I was hoping to share this morning with you the news that for the first time in US history, a woman was the next president. But I guess this hasn't happened. And as a scientist working for the past 20 years, all my career on building data-driven, machine learning-based of human behavior, the results are obviously extremely interesting to me because I'm sure that there is more research that we can do and better models that we can build. Because if we look at one of the latest polls from yesterday, the chances were clearly for Clinton, and in fact, Newsweek even dared to issue a number with Clinton as the next president. And as we all know, everything was wrong, right? So I think this is very interesting to me because, and it's been mentioned in the panel, we live in a world where increasingly we are modeling humans from data, and we are making decisions based on the results of those analyses. And what is clear is that humans, we are still unpredictable in a sense, and we are way more complex than we think we are. And also that we need to be very cautious about the data that we are using and understanding the limitations of that data. But I didn't come here to talk about data-driven models for predicting elections. I came here to talk to you about a topic that might be not as known to you, which is a lot of the work that we have been doing and other teams have been doing on understanding the value of big data to have positive social impact. I will describe work that we've done while I was at Telefonica. I'm no longer at Telefonica, but all the projects that I will present were projects that we did in my research team while I was at Telefonica. And in particular, when we talk about big data, there are many sources of data. A lot of them have nothing to do with humans. There is a lot of data about the universe, about particles colliding in an accelerator, et cetera. But a lot of the data is human behavioral data. And part of this data comes from a device that we all have in our pockets, which is our mobile phone. Because the reality is that the mobile phone is the most pervasive piece of technology in human history. The mobile phone penetration ranges between 90% and 120% worldwide. We love our phones. We spend more time with our phones than with anyone in our lives. This is important to think about. And the phone is connected, and it's really much more than a phone. In fact, many people don't even realize it's a phone because they don't talk with it anymore. And what is really relevant for this talk, this is a global phenomenon. This is a phenomenon happening everywhere, both in developing economies and in developed economies. And in the context of social good, most of the projects are done in developing economies. And the phone has become an incredible tool to be able to help those societies. In fact, in 2013, MIT Technology Review declared as one of the breakthrough technologies of 2013 the idea of using the data coming from chip phones, so coming from all phones, not just from smartphones, as one breakthrough technology that was going to enable us to really solve important problems or make better decisions. And I will illustrate this today during my talk. And as many of you might be aware of this, in the past couple of years, United Nations has been really paying attention to the potential value of data in the context of the Sustainable Development Goals. So when they were trying to define the new 17 Sustainable Development Goals, they called for a data revolution. And they commissioned a panel of experts, and one of them was actually my PhD advisor at MIT, to issue a white paper that would help them understand the potential of data and big data to both reach the 17 development goals and also measure whether we have achieved them or not. Because one of the challenges is not just achieving them, is that when you say we want to eradicate poverty, how do you measure poverty? How do you know that you have eradicated poverty? So both for measuring the goals and for achieving the goals, there is an opportunity to use large-scale data to help. So in my research team at Telefonica, for the past 8 years, we've been trying to answer the question on the slide. Could we use mobile digital footprints to help the world, both individually as individuals, and I'm going to talk about this today, but also the world at large? And this is a very abstract question, so I'll try to sort of like bring it down to earth in my presentation. As I mentioned, we are not the only people. There is an entire new field in computer science called computational social sciences, which has emerged as the combination of large-scale human behavioral data and social sciences and sociology as the new way of doing social sciences, where for the first time in human history, we are able to quantify large-scale human behavior. And this is something that we've never been able to do before. So a lot of social science theories were based on anecdotal evidence or on intuitions. But today, thanks to the existence of technology, we can actually verify or not those social theories. I'm going to very quickly give you an overview of how phone works, just to make it more clear the type of data that I'm talking about. But I imagine all of you know this. So this is a simplification of how a phone would see the world. So the phone needs to be connected to a cell tower. It's usually called a BTS. And the cell towers are all over the space. You can see them outside when you go to the cities. You see the little antennas. So usually, and this is a simplification, it's more complex than this, but in most projects, this is how we do it. We divide the space. We do what is called a Voronoi tessellation of the space, where we divide the space in these irregular cells such that at the center of each cell, there is a cell tower. And all the phones that are connected to the cell tower here are assumed to be here, but there is a fair amount of spatial uncertainty because the size of this cell tower, of these cells, is proportional to the density of cell towers, which is proportional to the density of population. So in urban areas, it could be 100 meter by 100 meter. In rural areas, it could be a few kilometers by a few kilometers. So we are not talking about GPS precision or all, but still is some rough sense of location. Temporally, the data that is typically used for these projects is also very imprecise because it's an event-driven data. So it's not data that is being collected continuously. It's only recorded when the phone is being used, either when the phone is making a phone call, receiving a phone call, or sending or receiving an SMS. So the most common data that is used for a lot of these projects is anonymized and aggregated CDRs, which you might have heard of, which are these records that are generated when the phone makes a phone call or receives a phone call or sends an SMS and receives an SMS. And the fields that are usually employed are the encrypted originating phone, destination phone, and then the location of the tower, if it's known. In many cases, it's not known. For example, if it's from a different operator. And for phone calls, also the duration of the phone call. So it's fairly coarse data, and it's always done in an aggregated manner. I'm just going to show you two videos so you get a sense of how this data looks like. The first video shows every bubble here is proportional. The size of the bubble is proportional to the number of phone calls that a cell tower is handling in that moment in time. And this is the state of Oaxaca, Mexico, right before, during, and after an earthquake takes place. And the epicenter of the earthquake will be here. So so pay attention to what happens when the earthquake takes place. So here's the epicenter, and then there's this big surge of phone calls. So the fact that there is this big surge of phone calls is extremely valuable, because when the government needs to send help, or when an NGO needs to send help, thanks to the fact that there is this surge, we can have an estimation of roughly how many people are in the affected areas so they can dimension the help appropriately. And this is something that we have never been able to do before. If we look at the mobility of phones, then we get a sense of mobility, of large-scale mobility between cities, which is also very valuable in some scenarios, for example, for public health. So using this type of data, which is very coarse, very aggregated, and seemingly useless, we actually are finding that it brings a lot of value in a number of scenarios. And the 4 scenarios that we have explored at Telefonica, where the first one is how can we use this data for helping design the cities better or understand how cities are working. The second scenario is how can we help in the case of official statistics, and this is an active discussion that is happening right now in most official statistics offices worldwide. How can we use new data sources to have more up-to-date censuses that we have now, because usually they are 10 years apart, and as you all know, society is very dynamic, and information from 10 years ago or even from 2 years ago is probably not applicable today. The third area is crisis management tools, as the example that I showed for the earthquake. And the fourth area is public health tools, and particularly in the context of pandemics, where human mobility is critical, and for the first time, we can model human mobility thanks to this type of data. So now, I don't have the time to give you an example of 4 different projects on these categories. So to keep with the spirit of the election, I'm gonna ask for a vote. So I'm gonna give you 4 options, and then I'm gonna ask you to raise your hand, and whichever winner it is, I'll explain that project like in 5 or 10 minutes. So the first project that I could talk about is a project of how we use this data to understand how effective the Mexican government measures were during the H1N1 flu pandemic. The second project is a project that we did to predict crime hotspots in London's metropolitan area. Third project is a project that we did 2 projects, but I can only talk one. We did one on inferring socioeconomic status in a developing country, and another one on inferring credit score to help the unbanked access credit in a developing country. And the fourth one is similar to the earthquake one, but it's in the context of floodings in Mexico in collaboration with the government of Mexico and United Nations. So, votes for the pandemic one? Wow, not that many. Votes for the crime one? Votes for the credit one? A little bit less. And votes for the natural disaster? Okay, so crime it is. So it's the only project that is not in a developing economy. Here we go. So this project was done in the context of a data-thon for social good that Telefonica organized. And it's a project in collaboration with MIT, with FPK, and with the University of Trento and with Data Pop Alliance, where I'm actually chief data scientist right now, which is a nonprofit focused on how to use big data to help development and to help the world. As you all know, crime affects the quality of life of the area where the crime is happening. There have been a lot of studies that have tried to find relationships between different socioeconomic indicators or census indicators and crime, like unemployment, and ethnicity, and education levels, and so forth. And in the past years, you might also know there has been movement towards focusing on place-centric models of crime as opposed to people-centric models of crime. So there's been the realization, and I think you all can empirically prove to that, that crime tends to be concentrated in certain areas in space. And most cities have safe neighborhoods and not so safe neighborhoods. So there is this concept of a crime hotspot, which is a location in space, an area in space that tends to have higher crimes than other areas. In terms of theories to explain crime and the relationship between crime and the urban environment, I'm going to describe 2 theories because they seem to be opposed, and we actually tried to figure out who was right in this project. So the first theory are the theories of Jane Jacobs. I don't know if you've heard of Jane Jacobs, anyone? So she was a social activist in the 60s, and she did a lot of work on trying to understand what made a city livable and what were the characteristics that made a city be a good place for people to be. And one of the topics that she discussed was crime. So she wrote a book called Eyes on the Street, and she talked about the fact that areas that have a lot of diversity and that have a lot of people moving are safer areas because we all act as sort of like policemen of each other. That's why she talks about eyes on the street. So we all protect each other by looking and seeing what's happening. But about 10 years later, Newman proposed the opposite theory in a sense, called the defensible space theory, where he said, well, places that have a lot of movement and a lot of people are less safe because they're more anonymous. So then people are less protected, so we should have these defensible spaces where everyone knows each other, like gated communities, where all the neighbors know each other, and that way it would be safer. So one of the questions is, so who was right? Because they seem to be saying different things. And as I said, all these theories until now have been very difficult to prove or disprove because we hadn't had access to large-scale human behavioral data. But today, we are able to start shedding some light on this. So I will tell you at the end of this project, we could shed some light on who was right, but I'll just do a quick poll. So who thinks Jane Jacobs was right? Just raise your hand. Not that many people. So who thinks Newman was right? more people. And I guess the rest of the people, you have your own theory, which is not here. So anyways, so as I also mentioned, you can have a people-centric approach to crime where you're trying to predict if an individual is going to commit a crime. This is not what we're doing. Or you can have a place-centric perspective where you say, well, I want to know whether this neighborhood is going to be safe or not. And that's what we are doing. And this is a very important distinction because when we made this project, it made it to the press, and most of the headlines were Minority Report, this and that, and it has nothing to do with like the Minority Report perspective. So it is a data-driven approach. We're going to be using data. It's a place-centric approach. We're going to be using multiple sources of data, so it's a multimodal approach. And the goal is to predict crime hotspots in the metropolitan area of London. So the reason why it's in London is because this project was part of a datathon that Telefonica organized. It was a datathon for social good, where large-scale, anonymized, and aggregated data was shared with research teams from all over the world that could explore how this data could be used for social good. And there wasn't only the mobile data that was shared, there was also data shared, because it was in collaboration with the Open Data Institute, there was also data that was shared coming from the Open Data Institute, a lot of census data and London data, that open data. For this particular project, we used 3 data sets. We used a mobile data set that we call the Smart Steps data set because it comes from a product that Telefonica had in the UK. We had the criminal cases data set, which was a data set shared by the London police, where it had the number of crimes in the metropolitan area of London for 2 months. And then the London Borough Profiles data set, which is the census sort of like data set. It has 64 indicators of census type of information. So I'll quickly explain each data set. So the Smart Steps data set was a data set coming from this product, where instead of dividing the space, as I showed before, in this irregular grid, now it's a regular grid, but it's the same idea. You have squares. The size of the square is proportional. It's inversely proportional to the density. So the higher the density, the smaller the square. And then for each square, and for every hour, what it was shared was an estimation of how many people were in that square in that hour, an estimation in percentages of what percentage of those people this was their home, their work, or they were visiting. And then a market research company also provided estimations on the gender splits and the age splits, because that data is not available just by looking at the activity in the cell towers, obviously. The crime data, as I mentioned, was shared by the London police, and it had 2 months of data, so we used 1 month for training the models and 1 month for testing the models. So there is an assumption that past behavior can predict future behavior, which, as I showed with elections, it might not always apply, but here it seems to work better. We need to define where a crime hotspot is, so we use the median value across the entire metropolitan area, and areas that had higher than the median were crime hotspots, and lower or equal than the median, they were not crime hotspots. And then I'm not gonna go into the details, but I mention it because all these things, they seem very simple and it's extremely hard. So the representation, the spatial representation is different between the census data and the crime data and the mobile data. So the mobile data has a grid, but the official data, the open data, has what is called the LSOA, that for you in the UK, you're probably familiar with this, which are the census regions that have a mean population of 1,500, and they're these very irregular kind of zip code kind of regions. So one important step is how you match both data sets to have the same representation. So for each of these LSOAs, we had access to the 68 metrics that are sort of like coming from the census, and which in the UK are very rich. We even have estimation of the happiness levels of the people in those LSOAs. But there is more typical demographic information, like age and income and the house prices and education levels and immigration levels and unemployment levels, etc. So the challenge is we built 3 different models. So the challenge is we either have the mobile data, or we have the census data, or we combine both. We have all the data, and what we want to do is we use this data for the month of December. We train the model with the month of December, and we want to predict which of these will be a crime hotspot in the month of January, and see if we are able to do this task, which is not even sure whether we can actually do it. So to do this, we need to first compute some features from the mobile data. So usually in these types of projects, you have a spatio-temporal series. And one of the questions is you don't know what is the right temporal granularity for the problem at hand. So is the number of people every hour the most important variable? Or is it the number of people in the mornings versus the evenings? Or is it the number of people every day? Or is it every week? Or is it every month? We don't know. So typically what you do is you compute a huge amount of features, thousands of features, all the features that you can imagine that could be meaningful for this problem. And then you apply feature selection techniques to identify which ones are the features that seem to matter the most for this problem. So in this problem, we computed up to 6,000 features originally, and then we applied a feature selection algorithm. In this case was the mean decrease of the Gini coefficient to go down to 68 features coming from the mobile data. And we chose 68 to have the same complexity in the model as the census data, because the census data were 68 variables. So at the end of this process, we had 68 features coming from the mobile data, 68 features coming from the census data, and then the ground truth for the crimes. And we built a model only using the mobile data to predict crimes, a model only using the census data to predict crimes, and a model that combined both to predict the crimes. And then the question is, how well can we do it and which one is doing better? So this is a binary classification approach. We use random forest. It's a state-of-the-art machine learning algorithm and that was performing better than other algorithms. And we got some surprising results. So I think the first surprising result is that the mobile phone data model was doing significantly better than the model using only the census data, which had about a 62% accuracy versus 68% accuracy, which was very surprising because the census data is very rich and very detailed data compared to the other data. And then when we combine both models, we reach almost 70% accuracy, which is very clearly illustrated in these two slides, which compare the ground truth versus the predictions. I'm joking, I don't think you can really tell which one is doing better. But I think the most interesting element beyond that you can do it with 70% accuracy is when you start looking at which variables matter, because they start shedding light on what is really correlated with crimes. So when I talked about the fact that we don't know which temporal granularity matters, so we found that the features about the daily dynamics were the ones that were being selected above features of hourly dynamics or weekly dynamics or monthly dynamics. So it seems that the daily dynamics was important to predict the crime. Another observation, and this is like to reveal who was right, whether Jane Jacobs or Newman. So we found two evidences that support actually Jane Jacobs. So the couple people that thought she was right, we found some evidence for that. So the first one was that we found that the higher the number of residents, the higher the probability that there will be a crime hotspot. And this is a contrasting Newman's theory that was saying the opposite. And we also found that entropy-related features were actually correlated with lower crime. And entropy measures how predictable a variable is, which is somehow related to Jane Jacobs' theories of diversity and having a lot of mix of people. So these two findings seem to point in the direction that Jane Jacobs might have been right. We also looked into the joint model that had 68 features that were coming both from the mobile data and the census data. And one of the surprises there was that only 6 out of the 68 features were coming from the census. And the other 62 features were about human dynamics. So it seems that for this particular problem, human dynamics is very important. And then when we looked at which census variables were important, we found what maybe intuitively people could think is correlated, like unemployment levels or immigration levels. So this was one of the first projects that has been able to show the value of human dynamic data coming from, in this case, the passive mobile network to predict crime. So with this, I think I'm going to, I don't know if I have 5 more minutes or I should finish, organizers? Should I finish? Okay, so I'll just quickly finish. They're like, I just wanted to probably just leave you, so if you're interested, we have a lot of scientific publications about this, and many of the projects have appeared a lot in the press, and I'll just mention in 2 seconds some of the barriers, because this seems, that as I said, this seems very easy, but it's actually very hard. And there are a lot of barriers why we don't actually are using big data to have real positive impact, right now. This was a research project. It's not a real project that is being used. There are internal barriers. I don't know right now of any company that has a big data for social good department. So there are barriers. Usually, when this happens, there is an evangelist in the company, like myself or Nicolas Decote in Orange, that are really advocating for this. There are a lot of barriers related to the risk and benefit analysis and potential unintended consequences of some of these projects. For example, if you model migrations in a non-democratic country where the government happens to be prosecuting a certain group, then you could have an unintended consequence. And in fact, one of the important things is the creation of special panels and ethics panels to make sure that you can anticipate the maximum number of these unintended consequences. There are a lot of barriers related to social challenges as well, and related to making sure that this is a tool that will benefit everyone, and that we don't create a gap between the ones that have access to the data and the technology and the ones that don't, because this is precisely the opposite of what we're trying to do. There are many technical challenges that as an expert in this topic, I'm very excited about. There is loads of technical challenges that we still need to solve. There are privacy and security challenges as well. Even if the data is fully aggregated, fully anonymized, it's fundamental to have a very clear code of conduct on how to handle this data, clear ethics guidelines on how to handle the data, obviously protect the data, make sure that it's securely stored, and so forth. And finally, there are a lot of challenges in the way of working, because these projects are by nature multidisciplinary and multi-team. So we are collaborating with the United Nations or with the government or with the police, and we speak different languages. And we are computer scientists, and they are whatever, lawyers or whatever they are. So it's very important to make sure that we understand each other and we set the right expectations, and we actually have our agendas somehow be aligned. And that's not easy, but I think it's a fundamental and a completely necessary condition for these projects to become a reality. I'm not going to explain this. If you're curious, you can talk to me later. But I think the question that I leave you with is, how can we all responsibly make use of this opportunity? Because the opportunity is huge. And I think it would be a shame if we don't leverage it to actually have positive impact in the world. Thank you.